Hold your hand in front of your face. It feels solid and whole, and it is yours. Yet it is mostly empty space, built from a few kinds of particle that have not changed since the universe was minutes old, following a small set of rules that physicists have written on something close to a single page. That page is the standard model, and it is the most precisely tested idea in the history of science. It has predicted the outcome of experiment after experiment, sometimes to better than 1 part in a billion, and it is almost certainly unfinished. At a laboratory outside Geneva called CERN, in the decays of particles far too small to ever see, a handful of careful measurements have drifted from what that page predicts. If you like following an idea all the way down, consider subscribing and stay a while. Our question is a quiet one. What would it take to find the first real crack beneath the most successful theory we have, and have we found one yet? We will build the answer slowly, one step at a time, starting from the matter in your own hand. Look closely at the back of your hand. The skin, the fine hairs, the warmth underneath, all of it feels like one smooth, continuous thing. Press a fingertip against the desk and the surface pushes back, solid and certain. That solidity is real, and it is also a kind of trick because almost everything you just felt is empty space holding its shape. Zoom in on a patch of that skin and it breaks into cells, small enough that a few thousand would line up across the width of this letter. Zoom in on a single cell and it breaks again into molecules, long chains and rings of atoms linked together. Zoom in on one of those atoms, the carbon in your skin, or the oxygen in the water you're mostly made of, and you reach a tiny dense knot at the centre with a faint cloud around it. The knot is the nucleus, the cloud is the electrons, between them lies almost nothing. Scale one atom up until its nucleus is the size of a marble on the floor, and the nearest electron would drift somewhere out near the walls of a stadium, with bare space the whole way in between. That is the real texture of matter. Your hand is solid the way a fast-spinning fan is solid, full of motion and force rather than stuff you could pinch. Now go one step deeper, into the nucleus itself. It is built from protons and neutrons, packed close. For a long while, the proton and the neutron looked like the bottom of the ladder, the smallest beads on the string, the place where the splitting finally stopped. They are not the bottom. Each proton and each neutron is built from still smaller pieces called quarks, bound together 3 at a time and never seen alone. Here is the part worth sitting with. Those quarks come in only a couple of kinds inside you, an up quark and a down quark, and the electrons in the cloud are a single kind too. Take a proton, 2 up quarks and 1 down quark. Take a neutron, 2 down quarks and 1 up. Add the electron, and you have nearly the entire recipe for ordinary matter. 3 ingredients: your whole hand, the desk it rests on, the air around it, the distant star whose light reaches your window, all of it draws on the same tiny short list. It feels too simple, and in a way it is, because the full list of building blocks runs a little longer than 3. But the spirit holds. Nature does not use a different brick for every wall. It works the way a written language does, where a handful of letters, arranged and rearranged, carry every book ever printed. The richness lives in the arrangement, not in some endless catalogue of parts. This is the quiet promise underneath all of chemistry and biology and everything you have ever touched. The same up quarks and down quarks that sit in your fingertips sit in the iron core of the planet and in the oldest stars. They have not changed since the universe was minutes old. Whatever else is true, you're made of a small number of pieces, repeated past counting, following rules you can hold in your head. Physicists wrote those pieces and those rules into a single framework and gave it a name as plain as the idea: the Standard Model. It is a kind of parts list and a rule book bound together. Over the next stretch, we will lay that list out gently, one piece at a time, until the whole picture stands in front of you and you can see where it might be cracking. For now, keep one sentence with you. Everything you can touch is built from a short list of particles, the same ones everywhere, doing the same few things. The next question is simply what is on that list, and we will lay the pieces out one by one. Imagine spreading every kind of fundamental particle on a table in front of you, the way you might lay out the pieces of a board game before anyone moves. The first thing you would notice is that they fall into two natural piles, and the split between those piles runs through the whole of physics. In one pile sit the particles that things are made of. These are the bricks. The quarks belong here, and so do the electron and its quiet cousins. Stack them, bind them, and you get protons, atoms, molecules, mountains, people. Physicists call this pile the matter particles, and they share a deep family habit. They keep out of each other's way. Two of them will not sit in the exact same state at the same place. That stubbornness is why your hand does not sink through the table. The electrons in your skin refuse to share a seat with the electrons in the wood, and so the two surfaces hold each other up. In the other pile sit particles of a completely different character. These are not bricks, they are messengers. Their job is to carry the forces, to pass between the matter particles, and tell them how to move. When two electrons repel each other, nothing reaches across the gap and tugs. Instead, one electron sends a messenger, and the other catches it, and the catching is the push. Physicists call this pile the force carriers, and they are happy to pile up together in the same state, the way countless rays of light can overlap in a single bright beam without crowding. So the table has two halves, matter that takes up space and stacks into things, forces that get passed back and forth and hold those things together or pull them apart. Almost everything that follows is the story of how these two halves meet. The matter half is built with a strange and beautiful symmetry. The pieces come in three nearly identical sets, called generations. The first generation is the one you're made of: the up quark, the down quark, the electron, and a faint particle called the neutrino. The second generation repeats the pattern with heavier versions of each. The third repeats it again, heavier still. Same shapes, same roles, 3 times over, with only the weight changing. Nobody fully knows why nature bothered to make 3. The copies you do not need decay away in a flash, which is why your hand uses only the lightest set. The force half holds the messengers. There is the particle of light, which carries the electric and magnetic force. There is a set of particles that glue the quarks together inside every proton. There is a pair of heavier messengers that handle a stranger, rarer force, the one that lets a particle change from one kind into another. And there is one more piece, off to the side, which does not push or pull at all, but instead gives many of the others their weight. That last one took the longest to find. Lay it all out and the count is humbling. A handful of matter particles in 3 repeating sets, a handful of force carriers, one field that hands out mass. From that short roster, every atom in the universe is assembled, every chemical reaction runs, every star burns. The whole table fits on a single page, and physicists have tested that page harder than any idea in the history of science. The arrangement is so tidy that it almost looks designed, and that tidiness is part of why a small crack matters so much. When a parts list this clean starts to wobble, even slightly, it means something is missing from the list itself. Hold this much. There are things, and there are the forces between things, and the standard model is the catalogue of both. We will start filling that catalogue with the bricks you're made of, the quarks first. Picture a single proton, sitting at the heart of a hydrogen atom in a drop of water on your skin. From the outside it looks like one round thing with a positive charge. Step inside and the picture changes completely. The proton is not a solid ball. It is a churning interior with 3 small fixed travellers in it, 3 quarks swimming in a storm of energy that holds them in place. Quarks come in 6 kinds, and physicists, with their usual taste for plain names, call those kinds flavours. The 2 flavours you carry are the up quark and the down quark. The up quark holds a charge of +2/3, an odd fractional value you never meet in everyday life. The down quark holds -1/3. Add 2 ups and 1 down, the recipe for a proton, and the fractions snap together into a clean +1. Swap to 2 downs and 1 up, the recipe for a neutron, and they cancel exactly to 0. The whole numbers you learned for protons and neutrons are really these thirds, quietly adding up. The other 4 flavours are heavier and rarer. There is the charm quark and the strange quark, a step up in weight. There is the bottom quark, sometimes called beauty, heavier again, and the top quark, which is the heaviest of all the known particles, as massive as a whole atom of gold packed into a single point. The top quark was the last to be found, caught at Fermilab near Chicago in 1995, decades after the lighter flavours were known. These heavy quarks do not last. Make one in a collision, and it falls apart almost instantly into lighter pieces, which is why your everyday matter sticks to up and down. There is something the quarks do that no other particle does, and it shapes the whole story. They carry a second kind of charge, beyond the electric one, a charge that comes in 3 varieties, physicists labelled with colour names red, green and blue. The names are a code, not a description. Quarks are far too small to have any colour you could see. The point of the code is that a proton, to exist at all, has to be colourless. The 3 charges balancing the way 3 stage lights of those colours blend into plain white. This rule is strict, and it is the reason quarks are never found wandering on their own. That last fact is one of the strangest in physics, so it is worth slowing down on. Pull 2 quarks apart and the force between them does not fade with distance the way gravity or magnetism does. It stays strong, like a rubber band that pulls harder the more you stretch it. Keep pulling, and you pour in so much energy that the energy itself turns into a fresh pair of quarks, which snap onto the ends. You meant to isolate one quark, and instead you made 2 new particles. No one has ever held a single bare quark, and the rules say no one ever will. So the quark is a particle you can be sure of without ever seeing it alone. We know its charge, its weight, its colour rule, the way it locks into 3s, all from the debris of collisions and the steady arithmetic that those fractions obey. The up and the down build the core of every atom in your body. The charm, strange, bottom, and top fill out the family, heavier echoes that flash into being and vanish. Carry this with you. A proton is not a tiny marble, but a tight knot of 3 quarks that can never be untied. That knot is held by a force we have not met yet, the strongest in nature. Before we reach it, there is the other half of the matter family to meet, the particles that are not trapped inside anything, the ones that fly free. There is one piece of you that is not locked inside a nucleus, one piece you could, in principle, strip away and send across a room. It is the electron, and it is the most familiar particle in your life. Every time a light switch closes, or a screen lights up, or a nerve in your arm fires, electrons are moving. They sit in the outer cloud of every atom, and they do all the work of chemistry, reaching out to bind one atom to the next. Your whole body is held together by electrons holding hands. The electron carries a charge of -1, a clean whole number, which is part of why it sits so neatly in the picture. It is light, far lighter than a proton, about 2,000 times less massive, and as far as anyone can measure, it has no size at all. It behaves like a true point, a charge with no width, which sounds impossible until you accept that the small things simply do not work the way pebbles do. The electron has 2 heavier siblings, and meeting them is the moment the matter family starts to feel deliberately built. The first is the muon. It is an electron in every way that matters, same charge, same basic behaviour, except it is about 200 times heavier. Make one, and it lives for barely 2/millionths of a second before falling apart. The muon was discovered in the 1930s, in the rain of particles that cosmic rays make when they strike the upper air, and when it turned up, nobody had asked for it. The physicist Isidore Rabi famously greeted the news with a shrug of a question, asking who had ordered that. Nothing in the theory had called for a heavy copy of the electron, yet there it was. Then there is a third sibling, the tau, heavier still, heavier even than a proton, and shorter lived than the muon by far. 3 versions of the same particle, light, heavier, heaviest. This is the 3-generation pattern again, the one running through all of matter, and the electron family shows it most cleanly. Now for the faint ones. Alongside each of those three charged particles sits a partner so shy it almost is not there. These are the neutrinos, and they are the ghosts of the standard model. A neutrino has no electric charge and almost no mass, and it barely touches anything. Right now, trillions of neutrinos from the sun are passing through your body every second, through your hand, through the chair, through the planet, and out the far side, scarcely noticing that the Earth was in the way. To stop even half of them, you would need a wall of solid lead light years thick. They are the closest thing nature has to a particle made of nothing. Yet neutrinos are not quite nothing, and that single fact is a crack in its own right. The original standard model assumed they had exactly zero mass. Then experiments deep underground watched neutrinos change flavour in flight, an electron-type neutrino arriving as a muon type, which a truly massless particle could not do. So neutrinos do carry a sliver of mass, tiny but real, and the model as first written has no clean place to put it. We will come back to that gap. For now, just note that even the faintest members of the family already refuse to fit perfectly. So the matter side of the table is complete. 6 quarks, locked away in threes inside protons and neutrons, 6 leptons, the 3 charged ones you could hold in a beam, and the 3 neutrinos that slip through everything. 12 bricks in all, in 3 repeating sets, and from them every solid thing is built. Bricks alone do nothing. A pile of quarks and electrons is just a pile. What turns the pile into an atom, a chemistry, a world, is the forces between them, and a force, it turns out, is also a particle. That is where we go next. You have always been told that a force is a pull or a push that reaches across a gap. A magnet tugs a nail from a distance. The Earth holds the moon without a rope. It feels like an invisible hand stretching through empty space. That picture works for everyday life, and it is worth honouring, because it got physics a long way. But at the level of particles, it is not what is happening, and the truer picture is stranger and simpler at once. A force, in the standard model, is a particle being passed back and forth. Not a field of influence draped over space, but an actual exchange, one particle thrown and another caught. The throwing and the catching is the force. When 2 electrons repel, picture them not as 2 stones connected by a stretched spring, but as 2 skaters on ice, one tossing a heavy ball to the other. The skater who throws recoils backward. The skater who catches gets knocked back too. From a distance, with the ball too small to see, it looks exactly as if the 2 skaters pushed each other apart. There was never a hand between them. There was only the thrown thing. Stay with the skaters, because they carry you most of the way. 2 people, a tossed object, a mutual shove. It explains repulsion beautifully. 2 like charges flinging messengers and driving each other away. The image even tells you something about strength and range, because a heavier ball is harder to throw far, which hints, correctly, that heavier messengers make shorter range forces. Now find the edge of the picture, the place where the skaters fail you, because that edge is where the real physics lives. Tossing a ball can only push 2 people apart. It can never pull them together. Yet most of the forces that matter, the attraction between an electron and a proton, the grip that holds a nucleus, are pulls. Real particles manage to attract by exchange, and the skaters on ice simply cannot. The reason is that these messengers are not ordinary balls obeying the rules you watch on a pond. They are quantum particles, allowed to do things a thrown object cannot, including carrying momentum in a way that draws 2 partners inward rather than apart. The everyday image takes you to the doorway and then politely stops. The messengers have a family name. They are called the gauge bosons, and boson simply marks them as the agreeable pile-up-together kind of particle, as opposed to the stubborn, one-seat-only matter particles. Each force has its own messenger, or its own set. The particle of light carries one force. A set of 8 similar particles carries another. A pair of heavy ones carries a third. Each will get its own chapter, because each force has its own personality, its own range, its own strength. What ties them together is this single idea, that to feel a force is to be on the receiving end of a particle. Light warming your face is a stream of these messengers arriving. The solidity of the floor is messengers traded between electrons over and over, billions of times in less than a blink. Nothing crosses the gap but particles, and yet from particles alone you get magnetism, light, the binding of every atom, the burning of every star. This is one of the quiet turning points in how we understand the world. Forces are not a separate kind of thing layered on top of matter. They are made of particles too, just particles with a different job. The table has bricks and it has messengers, and both are equally real, equally physical. So when we speak of the electromagnetic force or the strong force in the chapters ahead, we are naming specific messengers and the rules they follow. The first one to meet is the most familiar of all, the messenger you are looking at right now, the particle of light itself. Sunlight is falling on your hand at this moment, and with it, gentle warmth. That light crossed 93 million miles of empty space to reach you, took about 8 minutes doing it, and arrived as a stream of particles. Each one is a photon, the particle of light, and the photon is the messenger of the most far-reaching force in your daily life, the electromagnetic force. Start with what that force does, because you already know it by feel. It is the push between two magnets. It is the crackle of static when you pull a sweater over your head. It is the reason an electron stays near a nucleus, the negative drawn to the positive. Electric and magnetic effects look like two separate things until you watch them closely, and then they turn out to be a single force wearing two faces. A moving electric charge makes a magnetic field. A changing magnetic field pushes electric charges. In the 1860s, the Scottish physicist James Clerk Maxwell wrote down a tidy set of equations that wove them into one, and the unified thing is electromagnetism. Maxwell's equations carried a hidden gift. They predicted that a wiggle in the electric and magnetic fields would ripple outward at one particular speed, and when he calculated that speed, it came out as the speed of light. Light, he realised, was not a separate phenomenon at all. Light is an electromagnetic ripple, the field itself trembling and carrying that tremble across space. The thing letting you read this and the thing holding atoms together are the same force. The photon is the particle form of that ripple. It carries no electric charge of its own and it has no mass, and the masslessness matters more than it sounds. A massless messenger can travel forever without slowing, which is why the electromagnetic force reaches across the entire universe. Light from galaxies billions of years old still arrives at our telescopes, faint but intact. Compare that to the cramped short-range forces inside the nucleus, whose messengers are heavy and whose reach stops at the edge of an atom's core. Lightness buys distance. The photon, weighing nothing, never has to stop. Here is the everyday picture to hold. Two charged particles trade photons the way two people might toss notes back and forth, and the trading is the force between them. When a magnet lifts a paperclip, photons are passing between the iron and the magnet, unseen, doing the lifting. When your phone screen glows, electrons in it are dropping to lower states and flinging out photons, and some of those photons land in your eye. The force, the light, the warmth, all of it is photons in flight. The everyday image of trading notes has a limit, and the limit is wonderful. Most of these traded photons can never be caught in a net. They are exchanged so briefly, borrowed and returned within the interaction, that they leave no separate trace. Physicists call them virtual photons, a slightly misleading word because their effect is entirely real. They are the carriers of the force even though you can never isolate one. Only sometimes does a photon break free and fly off as actual light, the kind you see. The same particle plays both roles, the hidden messenger of force and the visible beam. The theory that describes all of this, photons and charged particles and their endless exchange, is called quantum electrodynamics, and it is the most precisely tested theory humanity has ever built. Its predictions match experiment to better than 1 part in a billion, an agreement so fine it is like measuring the distance from here to the moon and being off by less than the width of a hair. That precision becomes important later because it sets the standard against which every wobble is judged. So the first force is mapped: electromagnetism, carried by the massless photon, reaching across all of space, binding electrons to nuclei and lighting the sky. It rules the outside of the atom, but it is helpless to explain the inside, the nucleus, where a far stronger force is at work. Look again at the nucleus, that tiny dense knot at the centre of every atom, and you run straight into a problem that should not have a solution. The nucleus is full of protons, and every proton carries a positive charge, and like charges shove each other away. Pack a dozen protons into a space smaller than a trillionth of a centimetre, and the electric repulsion between them is enormous, fierce enough that the whole bundle ought to blow itself apart in an instant. Yet nuclei sit there, stable, for billions of years. Something is holding them together against a force straining to tear them open. That something is the strongest force in nature, and physicists named it with refreshing honesty, the strong force. It is the grip that binds quarks into protons and neutrons, and then binds those protons and neutrons into a nucleus. At close range, it overwhelms electric repulsion completely. The messenger that carries it is called the gluon, and the name is exactly right, because the gluon is the glue. The gluon does for the strong force what the photon does for electromagnetism, but with a wild difference in personality. Recall that quarks carry that second kind of charge, the one labelled with colour names, red and green and blue. The gluon is what passes between quarks to bind them, the messenger of colour. Here is the twist that makes the strong force unlike any other. The photon, the carrier of electric force, has no electric charge of its own, so photons ignore each other. Gluons are not so polite. A gluon carries colour charge itself. The glue is sticky to its own kind. That single fact explains the strangest behaviour in all of particle physics, the one we touched on before, that a quark can never be pulled free. Because gluons attract gluons, the force between two quarks does not thin out with distance the way an electric force does. Stretch two quarks apart and the gluons between them gather into a tight tube, a kind of taut string of pure force. Pull harder, and you're not weakening the bond, you are stretching the string, storing more and more energy in it. Stretch it far enough, and the energy becomes so great that it converts into a brand new quark and antiquark, which snap onto the broken ends. You tried to free one quark, and instead you made a new particle. This trapping has a name, confinement, and it is why no one will ever hold a lone quark in their hand. There is a mirror to confinement, just as strange, that runs the other way. When quarks are jammed extremely close together, the strong force between them nearly switches off, and they rattle around almost free. The bond is loose up close and unbreakable far apart, the opposite of every spring you have ever felt. This odd freedom at short range was worked out in the 1970s by David Gross, Frank Wilczek, and David Politzer, who shared a Nobel Prize for it. It was so counterintuitive that proving it reshaped the field. There is one more gift the strong force hides, and it is personal to you. Most of your weight does not come from the quarks themselves. The quarks inside a proton are remarkably light. The vast bulk of a proton's mass is the energy of the gluons and the churning field binding those quarks, energy locked into the form of mass. So when you step on a scale, almost everything that number measures is not particle stuff but bound up energy, the strong force made solid. You are, in the most literal sense, mostly tension. The strong force rules the inside of the nucleus, fierce and short-ranged, holding the coloured quarks in their unbreakable knots. It is the second of the messengers mapped. There remains a third force, the quietest and most peculiar, one that does not push or pull or bind, but instead changes one particle into another. Light a candle, and somewhere inside the sun that lit the sky above it, a quieter thing is happening that no candle could do. Deep in the sun's core, a proton is turning into a neutron. A particle is not just moving or binding, it is changing its very identity, becoming a different kind of thing. This is the work of the third force, and it is unlike the other two in almost every way. Physicists call it the weak force, and the modest name hides how much it shapes the universe. The strong force binds, the electromagnetic force pushes and pulls, the weak force transforms, it reaches into a particle and changes its flavour, turning a down quark into an up quark, and in doing so turning a neutron into a proton. That single conversion is the first step in the chain that makes the sun shine. Without the weak force, two protons in the solar core could never merge into the heavier nuclei that release the sun's energy, and the sun would not burn at all. The light on your hand depends on a force whose whole job is to let one particle become another. You have met the weak force before without knowing its name. It is the engine of one kind of radioactivity. When a radioactive atom decays and spits out an electron, what has happened inside is that a neutron flipped to a proton, shedding the electron and a ghostly neutrino as it changed. The clicking of a Geiger counter is the sound of the weak force at work, particles transforming one by one. The steady tick that lets us date ancient bones and rocks runs on this same slow transformation. The messengers of the weak force are called the W boson and the Z boson, and they break the easy pattern of the other carriers in one crucial respect. The photon has no mass, the gluon has no mass. The W and Z bosons are heavy, each about 80 to 90 times the mass of a whole proton, staggeringly massive for a single particle. That heaviness is the reason the weak force is weak and short-ranged. A heavy messenger is hard to make and cannot travel far before it must be reabsorbed, so the force reaches only across distances smaller than a proton itself. The weak force is not feeble by nature. It is simply burdened, carrying messengers almost too heavy to throw. The W boson is the one that does the transforming. It carries electric charge, plus or minus 1, and when a down quark emits a W and becomes an up quark, the charge has to balance, which is exactly why an electron and a neutrino come flying out to settle the books. The Z boson is the neutral partner. It carries no charge and changes no flavours, but it lets particles brush against each other through the weak force without trading identities, a subtler interaction that took clever experiments to catch. Finding these messengers was a triumph of European physics. In 1983, at CERN outside Geneva, a team led by Carlo Rubbia, using a beam refined by Simon van der Meer, caught the W and Z bosons directly for the first time. The two men shared a Nobel Prize within 2 years, an unusually fast honour, because the find confirmed a prediction that had reorganised the whole field. That prediction is the next thread, and it is one of the most beautiful results in all of physics. The weak force, with its heavy messengers, and the electromagnetic force, with its weightless photon, look like total opposites. One is short and shy, the other endless and bright. Yet they are not two forces at all. They are two faces of a single deeper force, and the story of how that was discovered comes next. Two forces could hardly look more different. The electromagnetic force reaches across the entire universe, carried by a massless photon, lighting galaxies billions of light years away. The weak force barely reaches across a single proton, carried by messengers so heavy they can scarcely move. One is bright and infinite, the other is faint and cramped. Nothing about them suggests kinship, and yet, in one of the great unifications in science, they turned out to be the same force seen under different conditions. The idea took shape in the 1960s through the work of 3 physicists who built on one another, Sheldon Glashow, Steven Weinberg and Abdus Salam. Salam's path is worth a moment. He grew up in what is now Pakistan, rose through scholarship after scholarship, and became the first person from his country to win a Nobel Prize in science, working much of his life to open physics to the developing world. Weinberg, in the United States, wrote a short paper in 1967 that pulled the pieces into a single elegant frame. Glashow had laid groundwork years earlier. Together they argued that electromagnetism and the weak force were one thing, which they called the electroweak force. The claim sounds impossible at first because the two forces are so plainly unalike. the resolution is an idea worth holding gently in your mind. In the first instance after the Big Bang, when everything was unimaginably hot, the four messengers of the electroweak force, the photon, and the heavy W and Z bosons were all alike, all massless, all reaching equally far. There was no difference between them. The force was a single, seamless thing. Then the universe cooled, and as it cooled, a kind of hidden field switched on across all of space, and that field treated the messengers unequally. It clung to three of them, the W bosons and the Z boson, loading them with mass and slowing them and shrinking their reach to the size of a nucleus. It left the fourth, the photon, untouched and weightless, free to roam forever. One force had frozen into two. The split you see today is not built into the messengers themselves. It is a leftover of cooling, the way a smooth pond freezes into ice that looks nothing like the water it came from. This idea that a single symmetric force can hide itself as the world cools and appear as separate forces is one of the deepest in modern physics. The forces did not change their nature. The stage they act on changed and froze them into different roles. The electroweak theory made a daring, specific gamble. It predicted that the Z boson must exist, a neutral, weak messenger that no one had yet seen, and it predicted roughly how heavy the W and Z would be. For a while it was just elegant mathematics. Then in 1973, experiments at CERN found the first trace of the Z boson's quiet influence. Neutral, weak interactions exactly where the theory said they should be. A decade later, the W and Z themselves were caught directly. The masses matched. The gamble paid off. Glashow, Weinberg and Salam shared the Nobel Prize in 1979 before the heavy bosons were even seen, because the case was already that strong. The unification left one enormous question dangling, and it is the question that hangs over the whole next chapter. If a hidden field switched on as the universe cooled and gave the W and Z their mass, what is that field? Where is it now? Can it be found? The theory only worked if such a field truly existed, woven invisibly through every cubic inch of space, touching nearly every particle. For decades, it was the most important thing in physics that no one had ever detected. Its name is the Higgs field. Why does anything have mass at all? It is the kind of question a child asks and a physicist struggles to answer, because mass feels like the most basic property a thing can have. A bowling ball is heavy, a feather is light, and that seems to need no explanation. But at the level of particles, mass is not a given. It is something that has to be granted, and the granting is done by an invisible field that fills all of space, the Higgs field. The idea was worked out in 1964, most famously by Peter Higgs in Scotland, and at the same time by Robert Brute and François Englert in Belgium, and others. Higgs was a quiet man who spent much of his life slightly embarrassed at having a field named after him. His proposal answered the question left hanging by the electroweak theory, the puzzle of why the W and Z bosons are so heavy, while the photon weighs nothing. His answer was that space is not empty. It is filled, everywhere, with a field that particles must move through, and moving through it is what we feel as mass. Here is the picture that has carried this idea for decades. Imagine a famous person trying to cross a crowded room. People press in, slow them down, cluster around them at every step. The famous person can barely move, as if they had become heavy. Now imagine a stranger crossing the same room. The crowd ignores them, and they walk straight across, light and quick. The crowd is the Higgs field. The famous person is a particle that interacts strongly with the field, and so drags, and so is massive. The stranger is a particle that barely interacts, and so flies free, and so is light or massless. Mass, in this view, is not stuff inside a particle. It is how much the field clings to it as it passes. Stay with the crowded room, because it explains a great deal. The W and Z bosons interact strongly with the Higgs field, so they emerge heavy, which is why the weak force is short-ranged. The photon ignores the field entirely, stays massless, and so electromagnetism reaches forever. The top quark drags the most of all, which is why it is the heaviest particle known. Every particle's weight is set by how tightly the field holds it. Now find the edge of the picture, because the crowded room quietly misleads in one way. A real crowd only slows a thing that is already moving. The Higgs field does something deeper, giving mass even to a particle that is standing still, building the very resistance to being pushed that mass means. The crowd image gets you to the idea and then, like every good comparison, hands you off to the real physics, which is subtler than any room of people. There is one more layer, and it is where most of your own mass does not come from. Remember that the bulk of a proton's mass is the energy of the strong force binding its quarks, not the Higgs field at all. The Higgs gives the quarks and the electron their small intrinsic masses, but the heavy lifting in your body is done by binding energy. So the Higgs field explains why fundamental particles weigh anything, while the strong force explains why you weigh as much as you do. Both are needed, and they answer different parts of the same question. For decades, the Higgs field was a brilliant necessity with no direct proof. The whole Standard Model leaned on it. Every prediction worked only if the field was real and woven through all of space. But a field is hard to catch. To prove it existed, physicists needed to make it ripple, to strike the field hard enough that a single piece of it broke loose as a particle, the Higgs boson. Finding that particle would mean finding the field. That hunt is the next chapter. To prove the Higgs field was real, physicists had to make it flinch. A field that fills all of space cannot be seen directly, but it can, in principle, be disturbed. Strike it hard enough in one tiny spot, pour in enough energy in one place, and a single ripple of the field should break loose and travel as a particle of its own, the Higgs boson. Finding that one particle would be like finding a single drop flung up from an invisible ocean, proof that the ocean was there all along. The trouble was that making the field flinch took more energy than any machine on Earth could deliver for a very long time. The Higgs boson, the theory said, would be heavy, and it would be desperately rare, and it would fall apart almost the instant it formed, in less than 1/1000,000,000th of a second. You could never catch the particle itself. You could only catch its wreckage, the lighter particles it decays into, and read its brief existence backward from the debris. Worse, those same lighter particles pour out of ordinary collisions by the billions. So a real Higgs signal would be a faint pattern buried in a roaring crowd of lookalikes. This is why the search demanded the largest machine humanity has ever built, the Large Hadron Collider at CERN, a ring 17 miles around buried beneath the border of Switzerland and France. It smashes protons together at very nearly the speed of light, concentrating tremendous energy into points smaller than an atom, again and again, hundreds of millions of times each second. Most collisions produce nothing new. But once in many billions, the energy strikes the Higgs field hard enough to shake a boson loose. 2 enormous detectors watched for it, instruments the size of buildings called Atlas and CMS, designed and run by thousands of physicists from dozens of countries. Each works like an immense layered camera wrapped completely around the collision point, catching the sprays of debris and measuring their energy and paths. The 2 teams worked separately and kept their results hidden from each other, so that if both saw the same thing, no one could blame a shared mistake. On the 4th of July 2012, in a packed auditorium at CERN, both teams announced the same result. Each had found a new particle, weighing about 125 times as much as a proton, decaying exactly the way a Higgs boson should. Peter Higgs, then in his 80s, sat in the audience and wiped his eyes. He had proposed the field nearly half a century earlier and lived to see its particle pulled from the wreckage of trillions of collisions. The next year, he and François Englert shared the Nobel Prize. It is worth feeling the weight of what that discovery did. The Higgs boson was the last missing piece of the Standard Model, the final entry on the parts list. Every other particle had been found, every force mapped. The Higgs was the keystone, predicted decades before anyone could test it, and when the machine finally reached high enough, there it was, at the mass the theory allowed. A pencil and paper idea from 1964 had been confirmed by the largest experiment ever attempted. With that, the table was complete. The quarks and leptons, the photon and gluons, the W and Z bosons, and now the Higgs. Every box filled. It was a moment of total triumph, and also a strange one, because completing the model meant the model now had nothing left to predict for itself. Every piece was accounted for, and every test it faced, it passed. That flawless record is its own kind of problem, and it is where the unease begins. A theory that never fails sounds like a dream. For physicists hunting what lies beyond, it has felt more like a wall. There is a peculiar mood among the physicists who study the Standard Model, and it is not pure pride. It is closer to frustration. The model works too well. It has been tested in thousands of ways, across decades, in laboratories on several continents, and it keeps passing, again and again, often to an accuracy that beggars belief. You might think a theory this successful would be cause for celebration. Instead, many of the people who know it best half resent it, because its very perfection leaves them nowhere to go. Consider the precision. The magnetic strength of the electron has been measured and calculated independently, and the two numbers agree to 12 digits. To picture that, imagine measuring the distance across the United States and being wrong by less than the width of a human hair. That is the kind of agreement the Standard Model routinely produces. Prediction and experiment lock together so tightly that there seems to be no daylight between the theory and the world. This is not an accident of one lucky quantity. Again and again, physicists have proposed a new particle on paper, calculated its mass and behaviour, built a machine to look for it, and found it sitting almost exactly where the model said. The W and Z bosons predicted, then found at the masses foretold. The top quark, predicted from subtle effects long before it was seen, then caught at Fermilab at close to the expected weight. The Higgs boson, the most dramatic of all, predicted in 1964 and confirmed in 2012. The model does not just describe what we already know, it tells us where to dig, and the thing is there. There is a reason this becomes a problem rather than a joy. Physicists are nearly certain the Standard Model is incomplete. They have solid reasons, which we will come to for believing it cannot be the final word about the universe. So they go looking for the place where it breaks, the experiment that finally gives an answer the model cannot match. That break would be the doorway to deeper physics, the first glimpse of whatever lies beneath. And for decades, the model has refused to provide it. Every test comes back clean. The wall does not crack. This is the strange bind at the centre of the whole story. A failure would be a triumph, a discrepancy, a number that comes out wrong, a particle that misbehaves, would be the most exciting result in particle physics in half a century, because it would point the way forward. The theory's stubborn success is, for the people hunting beyond it, a kind of locked door. They are not trying to confirm the Standard Model one more time. They are trying, with enormous machines and exquisite care, to make it fail. So when a measurement drifts, even slightly, from what that famous page predicts, the field does not groan, it leans in. A wobble in a rare decay, a particle that seems a touch too heavy, a ratio that comes out a little off, any of these could be the long-awaited crack. The hope is not idle. It is grounded in deep reasons to expect that the model is hiding something, that beneath its flawless surface there must be more. To even recognise a crack, though, you have to know precisely what the Standard Model predicts, and you have to be able to tell a real deviation from random noise. That takes two things. It takes a machine powerful enough to make rare events happen, and it takes a careful, almost ruthless way of deciding when a strange result is real, and when it is just chance dressed up as a discovery. The machine comes first. To hunt for cracks in the most precise theory ever written, you need to collide matter harder than anywhere else in the universe nearby, and read what comes out. That machine sits under the fields outside Geneva, and it is worth understanding how it works. Outside Geneva, beneath quiet farmland and the foothills of the Jura Mountains, runs a circular tunnel 17 miles around. deep enough underground that the cows grazing above never sense it. Inside that ring sits the Large Hadron Collider, the most powerful particle accelerator ever built, and the closest thing we have to a machine for making cracks appear. Its whole purpose is to take ordinary protons, the same protons that sit in your hand, and hurl them at one another with such violence that just for an instant, conditions like the first moments of the universe flicker into being. The idea behind it is simple, even if the engineering is staggering. To study the smallest pieces of matter, you have to hit them hard, and the harder you hit, the smaller the pieces you can probe and the heavier the new particles you can create. This is because energy and mass are interchangeable, a fact captured in the most famous equation in physics, that energy equals mass times the speed of light squared. Pour enough energy into a tiny point and that energy can congeal into new, massive particles that did not exist a moment before. The collider is in a sense a machine for turning motion into matter. To reach the needed energy, the collider speeds protons up to a hair's breadth below the speed of light. They circle the ring 11,000 times every second, which means that in 1 second, a single proton travels a distance greater than from here to the moon, and most of the way back. Keeping them on that curved path takes thousands of giant magnets, wound from special wire that loses all resistance to electricity when chilled to nearly the coldest temperature possible, colder than the empty space between stars. The collider holds within it both the hottest tiny points humans have made and some of the coldest large volumes side by side. The protons do not travel as a smooth stream. They are gathered into tight bunches, each holding more than 100 billion protons, and the bunches race around the ring in two beams going opposite ways. At a few chosen spots, the two beams are steered into each other, and the bunches pass through one another like two swarms of bees crossing in midair. Most protons miss, but in each crossing, a handful collide head-on, and it is those rare head-on hits that matter. When two protons meet at that speed, they do not simply bounce. The energy of the impact briefly recreates the kind of densely packed energy that filled the universe a tiny fraction of a second after it began. Out of that energy, a spray of particles bursts forth, some of them kinds that have not existed naturally since the cosmos was newborn. Heavy quarks, W and Z bosons, and once in a great while a Higgs boson, all flickering into being and decaying almost at once. The collider does not find old particles lying around. It makes new ones from raw energy, and then watches them die. The scale of it is hard to take in. The full machine took decades to plan and build, drew on the work of thousands of engineers and physicists from over 100 countries, and runs on the cooperation of nations that do not always agree on much else. It is among the largest and most complex devices our species has ever assembled, built for the single purpose of looking closer than anyone ever has. But making the collisions is only half the task, and arguably the easier half. A spray of particles bursting out of a proton crash lasts less than a blink and scatters in all directions. To learn anything, you have to catch that spray, measure every piece of it, and reconstruct what happened from the wreckage. That job belongs to the detectors, and they are marvels in their own right. When two protons collide inside the Large Hadron Collider, the actual event is over before it begins, lasting a tiny fraction of a trillionth of a second, far too fast and far too small for any eye or camera to catch. What you can catch is the aftermath, the spray of particles flung outward from the crash. Reading that spray, turning a chaotic burst into a precise measurement, is the work of the detectors, and they are among the most intricate instruments ever made. Picture one of them, the detector called Atlas. It is not a small device you peer into. It is the size of a cathedral, 150 feet long, weighing as much as 100 jumbo jets, built in layers wrapped completely around the point where the protons meet. The collision happens at the very center, and the debris flies outward in every direction, passing through shell after shell of the detector, each layer designed to catch a different kind of information. It works like an enormous camera that surrounds its subject on all sides at once, recording not a picture but the path, energy, and identity of every fragment. The layers each have a job. The innermost ones track the exact paths of charged particles as they curve through a powerful magnetic field, and the amount of curving reveals each particle's momentum, the way you might judge a car's speed from how sharply it can take a bend. Further out, dense blocks absorb particles entirely and measure the energy dumped when they stop, like catching a thrown ball in thick padding and feeling how hard it hit. The outermost layers catch muons, those heavy cousins of the electron which punch through everything else and are tagged as they leave. Piece the layers together and you can say, for a single collision, what came out, where it went, and how much energy it carried. The numbers are almost beyond grasping. The collisions happen 40 million times every second. No system on Earth could record them all, so the detector makes split-second decisions, throwing away the overwhelming majority of events as ordinary and keeping only the rare few that look interesting, a filtering called the trigger. Even after that brutal culling, the surviving data pours out in floods that fill vast computer farms and are shared with scientists across the globe to sift through. Finding one significant event can mean combing through trillions. There is a second giant detector called CMS, built on different principles by a different team, watching the same kind of collisions at another point on the ring. This doubling is deliberate and important. The two detectors are designed differently, run by separate collaborations of thousands, and they do not share their analyses as they work. When both see the same new thing, as they did with the Higgs boson, the agreement is powerful precisely because two independent instruments, with different possible flaws, arrived at the same answer. A mistake in one would be unlikely to be copied exactly by the other. What comes out of all this is not a photograph, but a reconstruction, a careful rebuilding of an event from the traces it left. From the tracks and energies, physicists work backward. They cannot see a Higgs boson, but they can see the particles it decayed into, measure their energies, and add them up to reveal the mass of the thing that produced them. The original particle is gone, but it leaves a signature in the arithmetic of its debris, and that signature is enough. So a collision becomes a measurement. A spray of fragments becomes a number, and here is where the deepest care of all is needed because nature is noisy, and random chance can mimic almost anything. A handful of collisions might, by pure luck, line up to look like a new particle that is not there. Before anyone can claim a discovery or a crack, they have to answer a hard question. How do you tell a real signal from a trick of chance? That question has a precise answer, and it is the rule by which all of this is judged. Flip a coin 10 times and get 7 heads, and you would shrug. That is ordinary luck, well within what chance produces. Flip it 100 times and get 70 heads, and you would start to wonder whether the coin was fair. Flip it 10,000 times and get 7,000 heads, and you would be certain something was wrong with the coin, because pure chance almost never strays that far. The whole art of deciding when a result is real rests on exactly this instinct, made precise. In particle physics, the measure of that instinct is called sigma. Sigma is a way of counting how far a result sits from what you would expect by accident. A small number of sigma means the result could easily be a fluke, the 7 heads in 10 kind of thing that happens all the time. A large number of sigma means the result is so far from ordinary chance that luck is a poor explanation, and something real is likely at work. The number grows as the gap between what you saw and what chance predicts widens, and as the amount of data behind it grows. It bundles the size of the effect and the weight of the evidence into a single figure. Physicists have settled on a strict threshold for announcing a true discovery, and it is called 5 sigma. A 5 sigma result is one so extreme that, if nothing real were there and only chance were at play, you would see a fluke this large about once in 3.5 million tries. That is the bar a new particle must clear before anyone is allowed to say it has been found. When the Higgs boson was announced, both teams had crossed 5 sigma, which is why the claim was made with such confidence. It was not a hunch, it was a number, agreed in advance, and the data had passed it. There is a softer threshold below that, 3 sigma, which physicists call evidence rather than discovery. A 3 sigma result would happen by chance only about once in 700 tries, which sounds convincing and often is not. The field has learned this lesson the hard way, over and over. 3 sigma bumps appear, excite everyone, and then melt away when more data arrives. They are interesting enough to chase and weak enough to vanish, and the gap between 3 sigma and 5 sigma is a graveyard of hopeful results that did not survive. Why set the bar so high? Because the experiments make so many measurements that flukes are guaranteed. When you look at millions of possible signals across countless collisions, some of them will line up by sheer accident, the way that, in a large enough crowd, someone is bound to share your birthday. A threshold of 5 sigma is the field's defense against fooling itself, a deliberately steep wall built because the temptation to see a discovery in random noise is so strong. The rule exists to protect physicists from their own hope. This is the lens through which every claimed crack must be viewed. When you hear that a measurement has reached 3 sigma, the right response is not excitement, but careful attention. It is a hint worth watching, not a result to trust. Many of the anomalies ahead in this story sit right in that uncertain band, strong enough to quicken the pulse, weak enough that more data might erase them. Knowing the difference between 3 sigma and 5 is the difference between a rumour and a fact. So we now have the full toolkit. A parts list, the standard model, tested to extraordinary precision, a machine, the collider, to make rare events happen, detectors to read the wreckage, and a rule, the 5 sigma standard, to judge what is real. With all of that in hand, we can finally ask the sharper question. The model is gloriously complete, and yet physicists are sure it is unfinished. What exactly can it not explain? For all its triumphs, the standard model has a short list of things it simply cannot say, and the list is not made of minor footnotes. These are not small gaps at the edges. They are vast, central features of the universe, sitting in plain view, and the most precisely tested theory in science has nothing to tell us about them. The completeness we have been admiring is, it turns out, a completeness within a small circle. Step outside that circle and the model goes silent. Start with something we already met. Neutrinos, those faint ghost particles that stream through your body by the trillions, were assumed in the original model to have no mass at all. But experiments deep underground, watching neutrinos arrive from the sun and from the upper atmosphere, found that they change flavour as they travel, an electron-type neutrino turning into another type in flight. That shape-shifting is only possible if neutrinos have at least a little mass. They do, and the standard model as first written has no natural slot for it. The discovery earned a Nobel Prize and quietly told us the model was missing something from the start. Then there is the matter of what the universe is mostly made of, and here the silence is deafening. When astronomers weigh galaxies by how fast they spin, the stars and gas we can see fall far short of the mass needed to hold them together. Something unseen, far more abundant than ordinary matter, is providing the extra pull. We call it dark matter, and it appears to outweigh all the ordinary matter, all the quarks and electrons in every star and planet and person, by more than 5 to 1. The standard model contains no particle that fits the bill. The stuff that dominates the mass of the cosmos is not on the parts list at all. There is a third absence, and it is the reason you exist to read this. In the hot early universe, matter and its mirror image, antimatter, should have been made in exactly equal amounts, and when matter meets antimatter, the two annihilate completely, leaving only light. Had the balance been perfect, the universe would now be a thin haze of radiation, with no stars, no planets, no people. Instead, a tiny surplus of matter survived. About 1 extra particle for every billion pairs, and everything you see is built from that leftover. The standard model includes a small lopsidedness between matter and antimatter, but nowhere near enough to explain the surplus. Why anything material exists at all is a question the model cannot fully answer, and there is one more, the largest of all. The model says nothing about gravity. The force that holds you to the floor, that shapes galaxies and bends light around stars, is simply absent from the framework. The other three forces are described in exquisite detail. Gravity, the one force everyone feels every second, has never been fit into the same picture. Our best theory of gravity, Einstein's, and our best theory of particles, the Standard Model, are written in different mathematical languages and have resisted every attempt to join them. So here is the real shape of things. The Standard Model is not wrong. Within its circle it is breathtakingly right, matching experiment to 12 digits. But the circle is small. It says nothing about dark matter, little about why matter beat antimatter, nothing about gravity, and it stumbled on the mass of the neutrino. These are not signs that the model is failing. They are signs that it is partial, a true description of one part of nature that must sit inside some larger, deeper theory we have not yet found. This is why physicists are so certain a crack must exist somewhere, waiting. The model is incomplete by these grand silences, and a deeper theory should leave fingerprints, small deviations in precise measurements, where the hidden physics leaks through. The hunt for those fingerprints is where the rest of this story lives, and it begins with a quiet rule the model insists upon, a rule about fairness among particles that experiments have started just barely to question. The Standard Model makes a promise so clean it almost sounds like a wish. It says that the three charged members of the lepton family, the electron, the muon and the tau, are treated exactly alike by every force, with a single exception. They differ only in mass. The muon is a heavy electron, the tau is heavier still. In every other respect, in how strongly they feel electromagnetism, how readily the weak force grabs them, how often a given process spits them out, the three are meant to be identical. Physicists call this rule lepton universality, and it is one of the deepest symmetries built into the theory. It is worth being clear about how strong a claim that is. The rule does not say the three particles are similar or roughly alike. It says the forces are blind to which one they are acting on. Set up the same situation for an electron and for a muon, and the weak force should seize each with precisely equal eagerness. Watch some particle decay in a way that can yield either an electron or a muon, and it should yield them in equal numbers once you correct for the small effect of their different weights. The universe is supposed to play no favourites among the leptons. Picture three siblings, identical in every skill, differing only in how much each one weighs. Give them the same tool and the same task, and they finish it the same way, by the same path in the same time. The only visible difference is that the heaviest is a touch slower to get going. That is lepton universality. The leptons are interchangeable workers, and the forces of nature are supposed to pay no attention to which one shows up for the job. Now find the place where this matters. Because the rule is so exact, it makes a perfect tripwire. Suppose some particle or force we have not yet discovered is out there, and suppose that hidden thing happens to care which lepton it touches. Then somewhere, in some careful count, electrons and muons would come out in unequal numbers. The symmetry would break, just slightly. And a broken symmetry that the Standard Model insists must hold would be a genuine crack, a direct sign of physics beyond the page. This is why lepton universality became such a prized hunting ground. It is not a vague expectation. It is a sharp prediction with a number attached, equal counts, and the theory commits to it fully, leaving no soft margin to retreat into. Either the leptons come out balanced as the model demands, or they do not. If they do not, something new is reaching into the process and tipping the scale toward one over the other. The image of identical siblings carries the idea, and it has one limit worth naming. Real siblings, however alike, carry countless small private differences. The leptons do not. As far as every experiment has ever shown, an electron and a muon are the same point of charge, the same in every property but mass, with no hidden quirks at all. The sameness is more perfect than anything in ordinary life, which is exactly why a measured difference would be so startling. So physicists went looking for a setting where electrons and muons are produced side by side, in numbers large enough to count precisely, in a process the model predicts with confidence. They needed a place where the books could be balanced to many decimal places, so that even a faint tilt would show. They found it in the decays of a particular heavy particle, one built around a heavy quark that falls apart in just the right way to put the rule to the test. That particle is the B meson, and it became the most sensitive laboratory in the whole search for a crack. To see why, we have to look at what a B meson is, and why its brief life reveals so much. A B meson is a small, short-lived particle, and its whole value to physics lies in how it is built and how it dies. Recall that quarks never travel alone. They bind into groups, and one common grouping is a quark paired with an antiquark, a partnership called a meson. A B meson is a meson built around the bottom quark, the heavy, rare flavour sometimes called beauty. Bind a bottom quark to a lighter antiquark and you have a B meson, a particle that does not exist in ordinary matter and must be manufactured in a collision. The bottom quark is heavy, far heavier than the up and down quarks you're made of, and heavy things in the particle world are unstable. A B meson lives for only about 1.5 trillionths of a second before it falls apart. In that flicker of existence it travels just a few millimeters, a tiny visible track, and then it decays into lighter particles. Everything interesting happens in that decay, in how the heavy bottom quark chooses to unravel. Here is why that unravelling is so revealing. A bottom quark cannot simply sit still. It must decay, and it can only decay through the weak force, the one force that changes a quark from one flavour into another. The weak force is feeble and slow, which means these decays are rare and unhurried, and rare unhurried processes are exactly the ones the standard model can predict with great precision. When a process happens easily and often, many tangled effects pile on and blur the prediction. When it happens reluctantly through a single narrow channel, the theory can state the odds cleanly. The B meson decays in just such a clean, reluctant way. Think of it like a very quiet room. In a noisy hall you could never hear a dropped pin. In a silent room the faintest sound carries. The rare decays of the B meson are that silence. Because so little is happening, the smallest unexpected contribution, the lightest touch of some new particle, would stand out against the quiet. A loud, common process drowns out newcomers. A rare one lets them whisper through. The room analogy has its edge, of course. A real room is silent because nothing is in it, while the B meson is quiet for a deeper reason, because the only door out is the narrow door of the weak force, and traffic through that door is naturally sparse. The silence is not emptiness, it is a bottleneck, and a bottleneck is precisely where a hidden influence would betray itself, by nudging the rare traffic up or down from what the theory allows. To use this laboratory, you need to make B mesons by the billions, and you need a detector built to catch their brief tracks and read their decays. CERN built exactly that. Alongside the giant ATLAS and CMS detectors on the collider ring sits a more specialized instrument called LHCb, the B standing for beauty. It is shaped differently from the others, stretched out to one side to catch the particles that fly forward from a collision, which is where the heavy quarks tend to go. Its single purpose is to study the decays of particles containing bottom quarks in enormous numbers with great care. Over years of running, LHCb has recorded the decays of staggering quantities of B mesons, building catalogues precise enough to test the model's predictions to a fine edge. And among all the ways a B meson can fall apart, a few particular decays are prized above the rest. They are the ones the standard model predicts most sharply, the ones where a hidden particle would most easily show its hand. Those decays go by a strange name, borrowed from a bar bet, and they are where the search grew tense. Among all the ways a B meson can fall apart, one family of decays is especially prized, because the standard model predicts them with such confidence, and because they are so very rare. These are the decays where a bottom quark turns into a strange quark. The strange quark is the lighter flavour we met earlier, a step down in weight from the bottom. You might expect a heavy bottom quark to slide easily into a lighter strange quark, the way water runs downhill. It does not. In the standard model, that particular change is forbidden as a direct single step. The reason is a rule about how the weak force works. The weak force can change a quark's flavour, but only in certain ways, and a bottom quark turning straight into a strange quark, both carrying the same electric charge, is not one of the allowed direct moves. So the change cannot happen in one clean step. It can only happen by a detour, a roundabout path where the bottom quark briefly transforms into other particles, heavy ones that exist for the merest instant, which then rearrange themselves into a strange quark. The decay sneaks through a loop of fleeting virtual particles rather than walking through a front door. These looping decays carry one of the more charming names in physics. They are called penguin diagrams. The name has nothing to do with the physics and everything to do with a dart game. In the 1970s, the physicist John Ellis lost a bet in a pub and was challenged to work the word penguin into his next paper. He struggled with it for a while, then noticed that one of these looping diagrams drawn a certain way could be made to resemble a penguin standing upright. The name stuck, and serious physicists have been saying it with a straight face ever since. The penguin decays matter for one precise reason. Because the bottom quark can only reach the strange quark through a loop of heavy virtual particles, the decay is exquisitely sensitive to what kinds of particles are allowed to run in that loop. The standard model knows its own particles and predicts the rate with great accuracy. But if some unknown heavy particle exists, it too could slip into the loop, adding its own contribution and shifting the rate away from the prediction. The loop is a kind of net cast into the unknown. Anything heavy enough to be created only fleetingly, anything we have not yet discovered directly, could still leave a trace here by passing through the loop and changing how often the decay occurs. That is what makes these rare transitions such a sharp tool. A common decay would tell you little, because it is dominated by familiar physics and predicted only roughly. A penguin decay happens perhaps once in a million B-mesons, through a narrow looping path, predicted to fine precision and open to the influence of particles no one has seen. It is the silence and the bottleneck together, refined to a single, well-understood process. One particular penguin decay drew the most attention. In it, a B-meson decays into a lighter particle called a kaon, which is built around that newly made strange quark, together with a pair of leptons. And here the two threads of the story braid together. That pair of leptons can be two electrons, or it can be two muons. The standard model, through lepton universality, insists the two outcomes should occur equally often, once the tiny mass difference is accounted for. The penguin decay had become a place to test the promise of sameness directly. So physicists counted. They tallied how often the B-meson produced two muons, and how often it produced two electrons, and they formed a simple ratio of the two. If the model was right, that ratio should sit at 1. The number they got back did not. The measurement physicists made was, at heart, a piece of careful counting. Take a vast pile of these rare penguin decays, the ones where a B-meson falls apart into a kaon and a pair of leptons. Count how many times the pair came out as two muons. Count how many times it came out as two electrons. Divide the first count by the second. The result is a single number, and physicists gave it a short name, RK, the R for ratio, and the K for the kaon left behind. The standard model is unusually confident about what that number should be. Because of lepton universality, the rule that the forces treat electrons and muons identically, the muon decays and the electron decays should happen equally often. After a tiny correction for the muon being heavier, the predicted value of R-K is very close to 1, and the theory states this with almost no uncertainty. This is rare and precious. Most predictions in particle physics come wrapped in fuzz, in clouds of hard-to-calculate effects. RK is clean. The model says 1 plainly and stakes itself on it. When LHCb measured RK, the number came back low, Not 1, but closer to 85 hundredths. The muons were showing up less often than the electrons, fewer of them than the rule demanded. It was as if, in the silent room, the model said you would hear 2 equal taps, and instead one of them came back softer than it should. The gap was small in size but enormous in meaning, because the prediction had been so firm. A clean prediction of 1, met by a measured value clearly below 1, is the kind of thing that makes physicists sit up. To check whether this was a true pattern or a single odd result, they looked at a close relative of the same decay. Instead of an ordinary kaon, the B-meson can decay into an excited, slightly heavier version, which physicists write as K-star. The matching ratio is called RK-star, and the logic is identical. Count the muon pairs, count the electron pairs, take the ratio, compare to the prediction of 1. When they measured RK-star, it too came back low. 2 related measurements, both in the same direction, both showing fewer muons than the model allowed. This is what raised the temperature. A single anomaly is easy to dismiss as a fluke or a flaw. 2 separate but related decays leaning the same way is harder to wave off, and there was more around it. Other measurements of these penguin decays, not ratios but the detailed angles and rates at which the particles emerged, had also been drifting from their predictions, and in a way that fit the same story. A consistent picture seemed to be forming, in which muons were somehow being shortchanged, as if a hidden particle out there had a quiet preference for electrons over their heavier cousins. It is worth holding the caution in the same breath as the excitement. These were small effects, measured at the edge of what the data could resolve. The ratios were below 1, but the error bars were not tiny, and a true result and a statistical fluctuation can look much alike when the numbers are this delicate. Still, the coherence was striking. The flavor anomalies, as they came to be called, were the most tantalizing hint in years that lepton universality might genuinely be broken, that the standard model's clean promise of sameness might not hold. By the late 2010s, the pieces had accumulated to the point where LHCb could put a precise figure on how far RK stood from the prediction, and how unlikely it was to be mere chance. In 2021 they announced that number, and it landed at exactly the level that quickens a physicist's pulse without quite letting them celebrate. In March of 2021, the LHCb collaboration announced its most precise measurement yet of RK, the ratio of muon decays to electron decays in those rare penguin transitions. The measured value sat below 1, the muons still coming up short, and the team reported how far that result stood from the standard model's prediction. Expressed in the language of sigma we built earlier, the answer was 3.1 sigma. Recall what that number means. 3 sigma is the level physicists call evidence, the point at which a result would arise from pure chance only about once in 700 tries. It is well short of the 5 sigma bar required to claim a true discovery, the 1 in 3.5 million standard that the Higgs boson had to clear. 3.1 sigma is real enough to take seriously and weak enough to vanish. It is precisely the level that has launched 1,000 hopes and buried most of them. But it is also the strongest that the lepton universality anomaly had ever been, and it did not stand alone. That was the heart of the excitement. RK at 3.1 sigma was 1 stone, but it sat in a small pile of stones all leaning the same way. The companion ratio, RK star, was low. The detailed shapes of related penguin decays had been drifting off their predictions for years. Another rare decay, in which a B-meson collapses directly into 2 muons, was running slightly below the predicted rate. No single one of these was decisive. Together they sketched a consistent story, all of them whispering that muons were behaving as though some unknown influence touched them and left electrons alone. The field responded with intensity. Theorists who study what lies beyond the standard model had been waiting years for exactly this kind of coherent hint, and they poured out hundreds of papers proposing what the hidden influence might be. If muons really were being treated differently, then lepton universality was broken, and a broken universality demanded a new particle or a new force, something the model did not contain. For the first time in a long while, there was a concrete target, a specific pattern in real data that a new theory would have to explain. The anomaly had a shape, and the shape could be chased. It is easy, looking back, to feel the pull of that moment and to forget how often the field had been here before. 3 sigma is a familiar place. The graveyard of particle physics is full of 3 sigma results that glowed for a season and then faded as more data came in. Seasoned physicists said as much at the time, urging patience, reminding everyone that evidence is not discovery, and that the only cure for a 3 sigma hint is more measurement. The right posture was attention, not belief. Watch it, gather more data, and see whether the effect grows toward 5 sigma or shrinks toward nothing. Still, this hint felt different to many because of its coherence. It was not one lonely bump in one lonely channel. It was a pattern across several measurements, in the cleanest decays the model predicts, all pointing the same way, and all gathered by the one detector built specifically to study them. If any anomaly was going to be the long-awaited crack, this cluster of flavour results looked like the best candidate in a generation. The muons that came out too few might be the first visible sign of a deeper layer beneath the page. While the flavour anomaly built, a second and far older puzzle was reaching its own climax in a different laboratory, around a different particle. It also involved the muon, but in a completely different way, through a tiny wobble that physicists had been chasing for half a century. That wobble has its own long and patient history. The muon, that heavy cousin of the electron, behaves in one respect like a tiny spinning magnet. Like the electron, it carries a property called spin, and a spinning electric charge acts as a small bar magnet with a north and a south. Place such a tiny magnet in a strong magnetic field, and it does not simply line up. It wobbles the way a spinning top leans and circles rather than standing straight. The rate of that wobble is set by a number written as g, and that number sits at the centre of one of the longest and most patient measurements in the history of physics. Simple theory, worked out long ago, predicted that g should equal exactly 2. The reality is a hair more. Quantum effects, the constant flicker of virtual particles around the muon, nudge g slightly above 2, and the small leftover, g minus 2, is what physicists set out to measure. It is a tiny quantity, a faint excess past a whole number, and pinning it down to many decimal places became a decades-long quest, passed from laboratory to laboratory like a relay baton. The chase began at CERN in the 1960s and 70s, with some of the first muon storage rings ever built, machines that held muons circling in a magnetic field long enough to watch them wobble. CERN measured G-2 more and more finely, confirming the basic prediction and laying the groundwork. Then the baton passed across the Atlantic to Brookhaven National Laboratory on Long Island, in the United States, where in the 1990s and early 2000s a dedicated experiment, built around a great circular magnet, pushed the precision further still. Brookhaven's result carried a quiet shock. The measured wobble sat a little higher than the theory predicted, by about 3 sigma, a gap small but stubborn, hinting that something unaccounted for was tugging on the muon. 3 sigma was tantalizing and not enough, and the experiment had reached the limit of what that magnet could do where it stood. So the relay made one of the most remarkable journeys in modern science. The heart of the Brookhaven experiment was its giant ring 50 feet across, and rather than build a new one, physicists decided to move the existing ring halfway across the country to Fermilab near Chicago, where a more intense muon beam awaited. In 2013, the ring travelled by barge down the eastern seaboard, around the tip of Florida, up rivers into the heartland, and then by truck across several states, a fragile circle of metal that could not be flexed more than a fraction of an inch without ruin. Crowds came out to watch it pass on the highway at night. At Fermilab, the ring was rebuilt, refined, and fed a far cleaner beam of muons, and the experiment began again with the goal of sharpening the measurement until any gap with theory became undeniable. In 2021 came the first result, and it confirmed the old Brookhaven anomaly, the muon still wobbling slightly faster than predicted. Combined with the earlier data, the gap stood at about 4.2 sigma, closer than ever to the discovery line. More data followed in 2023, tightening the measurement further. And in June of 2025, the collaboration released its final result, the most precise it would ever make: the muon's magnetism pinned down to 127 parts in a billion, a measurement so fine it earned the team a major physics prize. The measured wobble was now nailed down with extraordinary care, the product of 60 years of patient work across 3 laboratories and 1 improbable cross-country voyage. What remained was to understand exactly what that tiny excess past the number 2 could be telling us, and why a digit so far past the decimal point might hide entire undiscovered particles. To understand why the muon's tiny wobble matters so much, you have to picture what surrounds the muon as it spins. Empty space is not truly empty. The rules of quantum physics allow particles to flicker into existence and vanish again in fantastically short instants, a constant fizz of fleeting particles popping up and dissolving everywhere, including in the space immediately around the muon. This is not a metaphor. This restless cloud of momentary particles is real, and it touches the muon, and it changes very slightly how the muon's little magnet responds to a field. The cloud is what pushes G above 2. Here is the crucial part. Every kind of particle that exists contributes to that cloud. The muon is surrounded by flickering electrons, photons, quarks, every member of the standard model taking its turn appearing and disappearing, each one nudging the wobble by a precise calculable amount. So the measured value of G-2 is, in effect, a census. It adds up the influence of everything in nature that can briefly touch the muon. Measure it precisely enough, and you're counting the contributions of all the particles that exist. That is what makes a far-off decimal so powerful. Suppose there is a particle we have not yet discovered, too heavy to make directly even in the collider. It would still join the cloud, flickering around the muon for an instant like all the rest, adding its own small push to the wobble. We could never see that particle face to face, but it would leave a fingerprint in G-2, shifting the measured value away from what we calculate using only the known particles. A gap between measurement and prediction would be the silhouette of the unknown, the sum of everything we have left off the list. This is why a single digit, 11 or 12 places past the decimal, can in principle reveal whole new physics. The catch lives entirely on the prediction side, and it is a hard one. To know whether the measured wobble is anomalous, you must calculate, using only the known particles, exactly what G-2 should be, to the same staggering precision. Most of that calculation is under firm control. But one piece is brutally difficult, the part involving the strong force and its churning quarks and gluons fizzing in the cloud. The strong force, as we saw, does not yield to simple calculation, and this hadronic piece is the largest source of uncertainty in the whole prediction. Get it slightly wrong, and a real gap could appear or vanish on paper alone. There are 2 ways to pin down that stubborn piece, and they have not agreed. One way is data-driven, using measurements from other experiments, collisions of electrons and their antiparticles, to stand in for the hard-to-calculate part. The other way is to compute it directly from first principles on enormous supercomputers, a method called lattice calculation. For years, the data-driven approach gave the prediction that made the muon's wobble look anomalous, the famous 4 sigma-ish gap. Then the supercomputer calculations began to disagree, returning a prediction noticeably higher, one that sat much closer to the measured value and left little room for new physics at all. In 2025, the community's best collective estimate shifted toward the supercomputer result, and the celebrated gap narrowed sharply. The measurement itself is rock solid, the finest ever made. But whether it signals a crack now hangs on a calculation that has moved toward the model, not away from it. The muon's wobble is real and beautifully measured, and the question of whether it points beyond the standard model has quietly become a question about a number we're still learning to compute. So the muon offered 2 separate hopes, the flavor ratios and the wobble, and both proved delicate. There was a third hint, around a different particle entirely that for a time looked like the boldest crack of all. The third major hint came not from the Muon, but from the W boson, that heavy messenger of the weak force we met earlier. The W boson has a mass, a definite weight, and in the standard model that weight is not free to be anything. It is tied tightly to the rest of the theory. The mass of the W is woven together with the mass of the Z boson, the mass of the top quark, the mass of the Higgs, and the strength of the electroweak force. Fix those, and the model tells you what the W must weigh with real precision. The prediction comes out at about 80,357 in the units physicists use for these masses. This makes the W boson's mass a powerful test. If you measure it and get the predicted value, the whole interlocking structure of the model holds together, every piece consistent with every other. But if you measure it and get something else, even slightly off, then the pieces do not fit, and the misfit could only be explained by something new, some undiscovered heavy particle subtly altering the W through the same kind of quantum cloud that surrounds the Muon. A wrongly weighted W would be a crack in the model's internal consistency. In April of 2022, a collaboration called CDF, working with Delta from the Tevatron, an older collider at Fermilab that had since shut down, announced the most precise measurement of the W boson's mass ever made. They had spent years on it, combing through their data with enormous care, and the value they reported was not 80,357. It was about 80,433, heavier than the prediction by a clear margin. In the language of sigma, the gap stood at roughly 7, far beyond the 5 sigma discovery threshold. On its face, this was the boldest anomaly of all, a precise measurement standing 7 sigma from the standard model. A 7 sigma result should be earth-shaking, and for a moment it was. But a single measurement, however careful, is not the final word, especially when it stands against others. And here is where the W mass story turned. Other experiments had measured the same quantity, and they did not agree with CDF. An earlier measurement from the Atlas detector at CERN, refined after the CDF result appeared, came back consistent with the model. A measurement from LHCb leaned toward the model too, and then in 2024 the CMS collaboration at CERN released its own painstaking measurement, nearly as precise as CDF's, after almost a decade of work. It found the W boson sitting right where the standard model said it should, so the picture was not one measurement against a prediction. It was one measurement, the CDF result standing high and alone against a prediction and several other measurements that all agreed with one another. The most likely explanation, in the view of much of the field, is not a new particle, but some subtle, unidentified flaw in the CDF analysis, a systematic effect that pushed their number too high. The CDF team stands by its work, and cross-checks have not overturned it, so the result has not been simply discarded. But a single outlier among agreeing measurements is a weak foundation for a crack. This is the sober pattern that runs through all 3 hints. Each looked, for a season, like it might be the doorway beyond the model, and each, on closer inspection, grew fragile. Yet the very fact that physicists built specific new particles to explain them is worth examining, because those invented suspects tell you what a real crack might actually look like. When a measurement drifts from the standard model, theorists do not merely note the gap. They ask what could cause it, and they invent candidate particles, designed on paper to produce exactly the observed effect. These invented suspects are not idle guesses. They are constrained, shaped to fit the data, and the same few keep appearing because only a few kinds of new particle could produce the pattern seen. 2 suspects dominated the hunt for the flavor anomalies, and they are worth meeting because they show what the missing piece of the model might be. The first is called a leptoquark, and its name tells you what it does. The matter particles, you will remember, fall into 2 families that never mix: the quarks, locked inside protons and neutrons, and the leptons, the electron and its kin that fly free. In the standard model, nothing turns one family into the other. A quark stays a quark, a lepton stays a lepton. a leptoquark would break that wall. It is a hypothetical heavy particle that can absorb a quark and emit a lepton, or the reverse, a bridge between the two families that the model keeps strictly apart. If a leptoquark existed and happened to couple more strongly to muons than to electrons, it could slip into the loop of a penguin decay and tip the muon count downward, producing exactly the kind of low RK that LHCb saw. The second suspect is called a Z prime, and it is a heavier echo of a particle we already know. The Z boson, the neutral messenger of the weak force, carries one of nature's forces between particles. A Z prime would be a second, heavier version of it, the messenger of a new force we have not yet discovered, similar in character but distinct. The key is that this new force could be choosy, coupling to muons differently than to electrons, breaking lepton universality directly. A Z prime tuned the right way would also pull RK below 1, treating the two leptons unequally where the model insists they be equal. Notice what both suspects have in common. Each is a heavy particle, too massive to have been produced directly so far, but light enough to leave fingerprints in the rare decays through the quantum cloud. Each was reverse engineered from the data, built to explain a specific anomaly, rather than dreamed up first and tested later. This is a respectable way to work, and it is also a cautionary one, because a particle invented to fit one wobble can always be adjusted to fit a slightly different wobble, and a theory bent to match every shift in the data is hard to ever rule out. Neither suspect has been found. Searches at the collider for direct signs of leptoquarks and Z prime bosons have come up empty, pushing their possible masses higher and higher into ranges where they would barely be able to explain the anomalies at all. The suspects remain possible but cornered, squeezed by the absence of any direct sighting, and when the flavor anomaly that called them into being later weakened, much of their reason for existing weakened too. Still, the exercise reveals something true about how a real crack would unfold. It would not arrive as a vague sense that the model is wrong. It would arrive as a specific deviation, pointing to a specific kind of particle, which experimenters would then hunt directly. The leptoquark and the Z prime are templates for that process, the shape of what discovery would feel like. There is one more proposed extension to the standard model, far grander than any single suspect, that physicists believed in for decades with something close to faith. Its elegance made it the favourite, and its long, total absence from the data has become one of the most telling silences in modern physics. For nearly 40 years, the favoured guess about what lay beyond the standard model was a sweeping idea called supersymmetry. It was not a single particle, but a whole new symmetry of nature, and its beauty won over a generation of physicists. The proposal is this: for every known particle there exists a heavier partner, a kind of mirror twin. The electron would have a partner, the quark would have a partner, the photon and the gluon, and the Higgs would each have one. A whole shadow roster doubling the table, every familiar particle matched to a so far unseen heavier companion. The appeal was not the doubling for its own sake. Supersymmetry solves several deep problems at once, and that is what made it so seductive. It would explain why the Higgs boson is as light as it is, taming a calculation that otherwise suggests the Higgs should be enormously heavier, a long-standing puzzle physicists call the hierarchy problem. It would let the strengths of the three forces, which differ so much at everyday scales, converge to a single value at very high energies, hinting at a deeper unification. And the lightest of the new partners, stable and invisible, would be a perfect candidate for dark matter, the unseen stuff that outweighs everything we can see. One idea, three great problems eased. It was hard not to believe in something so elegant. So when the Large Hadron Collider switched on, many physicists expected it to find supersymmetry quickly. The partners, if they existed at the masses the theory favoured, should be produced in the collisions and show up in the debris. The most natural versions of the idea, the ones that best solved the hierarchy problem, predicted partners light enough to appear early. Couriers were built on the expectation. Searches were designed and waiting before the first collisions ever happened. The collider ran. The searchers combed the data, and nothing appeared. No partner for the electron, no partner for the quark, no sign of any superpartner at all. As the years passed and the data piled up, the searchers pushed the possible masses of these partners higher and higher, ruling out range after range. The light, natural versions of supersymmetry, the ones that solved the hierarchy problem cleanly, were steadily excluded. The partners, if they exist, must now be so heavy that they no longer do the elegant work the theory was admired for. This long absence is itself a profound result, though it is a quiet and disappointing one. The silence is data. It does not prove supersymmetry false, because the idea is flexible and can always be pushed to higher masses, retreating just beyond the reach of each new search. But it has forced a reckoning. The most compelling reason to expect new physics at the collider, the elegant solution that nearly everyone bet on, did not show up where it was supposed to. Nature, it seems, did not choose the beautiful answer, or at least not the version we found beautiful. There is a lesson in that silence, and it sharpens the whole story of the search for a crack. Elegance is not evidence. The universe is under no obligation to be tidy in the ways we find appealing. Supersymmetry was loved because it was clean and powerful, and its long failure to appear is a reminder that the next layer of physics may be stranger, uglier, or simply different from anything we have imagined. The model's silence on supersymmetry has humbled the field. The collider has produced other moments of hope that proved even more fleeting, none more famous than a bump in the data that arrived one winter and thrilled the entire field before vanishing within months. In late 2015, the two great detectors at CERN, Atlas and CMS, saw something in their fresh data that made the whole field hold its breath. Both detectors, independently, recorded more events than expected in which a collision produced two photons, two particles of light, flying out with their energies adding up to a particular value, around 750 in the units used for particle masses. A bump, in other words, an excess of events clustered at one mass, which is exactly what a new particle decaying into two photons would produce, and it appeared in both detectors at once. That last fact is what set hearts racing. A bump in one detector could easily be a fluke, a random pile-up of ordinary events. But two separate detectors, built differently, run by different teams, seeing an excess at the same mass, was far harder to dismiss. It was the same logic that had made the Higgs discovery convincing. When the Higgs was found, both detectors saw it, and no one could blame a shared mistake. Now both detectors were seeing something at 750, and the natural thought was that history might be repeating, that a genuinely new particle had just announced itself. The response was extraordinary, and in hindsight a little feverish. Within months, theorists wrote hundreds of papers, by some counts more than 500, each proposing what the new particle at 750 might be. It could be a heavier cousin of the Higgs. It could be a sign of extra dimensions of space. It could be a piece of some grander theory. The bump was real data sitting in both detectors, and an entire community rushed to explain it, to claim a piece of what looked like the most important discovery in decades. The air was thick with anticipation. Then more data came in. Through 2016, the collider kept running, the detectors kept recording, and the statistics grew. And as they grew, the bump did not. It did the opposite. With more collisions, the excess at 750 faded, shrank, and finally dissolved entirely, until there was nothing there at all. It had been a statistical fluctuation, an accident of chance that happened by bad luck, to appear in both detectors at the same mass at the same time. The hundreds of papers explaining it became explanations of nothing. The particle had never existed. It is worth sitting with how that happened, because it is the heart of the whole cautionary tale. The bump was not fraud or sloppiness. It was real data, honestly recorded, that simply turned out to be a coincidence. Random fluctuations are not rare when you look in enough places, and two detectors fluctuating up at the same spot, while unlikely, is not impossible. The field's hope had outrun its caution. People had treated a striking but unconfirmed signal as if it were nearly a discovery, and the universe quietly corrected them. The ghost at 750 became a kind of parable, told and retold as a warning. It showed how powerful the pull of a promising signal can be, how an entire community can lean into a hope before the evidence has earned it. It also showed the system working as it should, because the discipline of waiting for more data, of refusing to claim 5 sigma until it is truly reached, is exactly what exposed the bump as empty. The same rigour that protects against fooling ourselves is what dissolved the ghost. That parable points to a deeper statistical truth, one that explains why so many anomalies fade, and why even the most exciting of the flavour hints eventually softened back toward the very model it had seemed to challenge. There is a statistical trap that lies beneath nearly every fading anomaly, and once you understand it, the disappearance of so many hopeful signals stops being surprising. Physicists call it the look elsewhere effect, and the name captures it well. The danger comes from looking in many places at once. Consider what it means to search for a bump in the collider data. You do not look at a single point. You scan across a whole range of possible masses, examining hundreds or thousands of spots, asking at each one whether there is an excess. Now recall that random chance produces fluctuations everywhere. At any single spot, a fluctuation large enough to look interesting is unlikely. But across 1,000 spots, the odds that at least one of them throws up a striking fluctuation by pure chance become quite high. It is the birthday principle again. In a large enough crowd, someone almost certainly shares your birthday, even though for any one person it is improbable. So when you find a 3 sigma bump somewhere in a wide scan, you must ask not how unlikely that bump is on its own, but how unlikely it is that no such bump appeared anywhere in the whole range you searched. Account for all the places you looked, and a local 3 sigma excess often shrinks to something far less impressive, a fluctuation you should have half expected given how many chances you gave nature to fool you. This is why physicists distinguish between local significance, the bump taken alone, and global significance, the bump corrected for the breadth of the search. The global number is almost always smaller, and it is the honest one. The look elsewhere effect explains the 750 bump, which was less impressive once the full scan was accounted for, and it explains the general pattern of 3 sigma hints that glow and fade. But its sharpest lesson came from the flavour anomalies, the RK results that had looked like the best crack in a generation. In December of 2022, after years of work, the LHCb collaboration released a more complete and careful analysis of those very ratios, with a far better understanding of the backgrounds. The key turned out to be the electrons. Counting muons in these decays is relatively clean, but counting electrons is harder, because other ordinary particles can be mistaken for electrons in the detector, sneaking into the tally. In the earlier analysis, this contamination had been underestimated. There were not too few muons after all. There had been too many apparent electrons, ordinary particles masquerading as them, inflating the electron count and pushing the ratio below 1. When the backgrounds were properly accounted for, the muon and electron counts came back into balance. RK and RK star moved back up toward 1, exactly where the standard model said they should be. So the most exciting anomaly, the coherent flavour pattern that had launched hundreds of papers and revived the leptoquark and the Z prime, largely dissolved. Lepton universality held after all. The muons were never missing. The promise of sameness, that the forces treat electron and muon alike, survived its sharpest test. It was a deflating result for those who had hoped, and a triumph of careful method, the slow correction of an honest mistake by more data and harder work. This is the rhythm the field has learned to expect and to respect. Hints arrive, gather excitement, and then either harden into discovery or melt under scrutiny, and far more often they melt. It is not failure. It is how the search protects itself from believing too soon. But it leaves a pressing question. After RK faded and the bump vanished and supersymmetry stayed silent, of all the hints, which ones are still standing? After all the hints have been weighed, The honest tally is sobering and worth laying out plainly. Take them one at a time. The flavour anomaly, the low RK that had looked like the best crack in a generation, has faded. The fuller analysis pulled the ratios back to 1, lepton universality held, and the muons that seemed to be missing were never missing at all. That hint, the brightest of them, has largely dissolved into a corrected counting error. The bump at 750 is gone entirely, revealed as a fluctuation that vanished with more data. Supersymmetry, the elegant favourite, has never appeared, its natural versions excluded across vast ranges by searches that keep coming up empty. The W boson mass anomaly, the bold 7 sigma result from CDF, stands alone against the prediction and against every other measurement, including the precise one from CMS that agreed with the model. Most of the field reads the lone high value as a likely flaw in one analysis, rather than a sign of new physics, though the question is not formally closed. That leaves the muon's wobble, G-2, which is the most interesting survivor and also the most ambiguous. The measurement itself is magnificent, the finest ever made, pinned down to 127 parts in a billion after 60 years of work. There is no doubt about how fast the muon wobbles. The doubt lives entirely on the theory side, in that brutally hard piece of the prediction involving the strong force. For years, the data-driven prediction made the wobble look anomalous, a gap of around 4 sigma. Then the supercomputer calculations disagreed, returning a higher prediction much closer to the measurement, and in 2025 the community's best estimate shifted toward them. The famous gap narrowed. Whether the muon's wobble points beyond the model now hangs on a calculation still being refined, a number we are learning to compute rather than a clear crack in the data. There are smaller hints that persist at low significance, certain rates and angles in the penguin decays that still sit a little off, not yet pulled fully back into line. They are interesting enough to watch and far too weak to claim. None of them, alone or together, has reached the 5 sigma bar that a discovery requires. So the plain verdict, as things stand, is this. No single laboratory measurement has yet produced a confirmed crack beneath the standard model. The most dramatic candidates have faded or narrowed, and the survivors hover in the uncertain band, hints rather than facts. It would be easy to read that as defeat, and it is not. It is the search working as it must. The discipline that dissolved RK and exposed the 750 bump is the same discipline that would, one day, confirm a real crack and make it stick. A field that let 3 sigma hopes harden into beliefs would discover phantoms constantly and trust nothing. The graveyard of faded anomalies is not a sign of failure. It is the price of being sure, and being sure is the whole point. So at the level of direct measurement, the careful answer to the title's question is that we have not yet found a confirmed crack, only hints that have, so far, slipped away or grown murky on closer inspection. That is the honest state of the hunt inside the machine. But the hunt is not over, and it is about to enter a sharper phase. The collider is being upgraded to deliver far more collisions than ever before, and that flood of new data will take many of these wavering hints and force them, at last, toward a clear answer. The search for a crack is about to get sharper, and the reason is simple. The Large Hadron Collider is being rebuilt to deliver far more collisions than before. The upgrade is called the High Luminosity LHC, and luminosity in this context just means the rate at which collisions happen. The plan is not to raise the energy of each collision much, but to vastly increase how many collisions occur. Where the machine now produces a certain torrent of crashes, the upgraded version will produce many times more, packing the beams more tightly so that protons meet far more often at each crossing. More collisions matter, because the physics that interests us lives in the rare events. The penguin decays of B mesons happen perhaps once in a million. The production of a Higgs boson is rarer still. When the events you care about are needles in an enormous haystack, the only way to find more needles is to gather a far bigger haystack. The upgrade does exactly that. It will let the detectors record many times as many of the rare decays and rare productions, building the statistics that turn a fuzzy hint into a firm number. Recall what limits the current anomalies. They sit in the uncertain band, around 3 sigma or below, strong enough to notice and weak enough to fade, precisely because there are not yet enough events to tell signal from chance with confidence. A 3 sigma hint is a measurement with error bars too wide to settle the question. The cure for wide error bars is more data. Gather enough rare decays, and the error bars shrink, and the hint is forced to choose. Either it grows, climbing toward the 5 sigma discovery line as the effect stays real while the uncertainty falls, or it dissolves, the way RK dissolved, revealed as a fluctuation or a correctable error. The flood of new collisions will push many of today's wavering hints toward one fate or the other. The detectors themselves are being upgraded to handle the deluge. More collisions per crossing means more debris to untangle at once, a harder problem for the layered instruments, so Atlas and CMS and LHCb are being fitted with sharper, faster sensors able to keep up. The work spans years and the upgrade comes online gradually toward the end of this decade, after which the machine will run for many more years, accumulating a body of data that dwarfs everything collected so far. By the time it finishes, the haystack will be many times larger than the one that produced every result in this story. There is a longer horizon too. Physicists are already designing the colliders that might follow, vastly larger rings or machines that collide different particles, capable of reaching energies or precisions the current machine cannot. These are decades away and not yet certain to be built, but the planning reflects a settled conviction. The search will not stop with the present machine because the reasons to expect new physics do not depend on any single anomaly. They run deeper than the data. That is the key point as the hunt moves forward. Even if every current hint fades under the new flood of data, the conviction that a crack exists will not fade with them. The faded anomalies were only ever candidates, particular places where the crack might have shown. The belief that there is a crack somewhere rests on something far more solid. On the grand silences we met earlier, the things the model cannot explain no matter how precisely it is tested. Those silences are the real reason physicists are sure the page is unfinished. Set aside every laboratory anomaly for a moment, every faded bump and narrowed gap, and the conviction that the standard model is incomplete does not waver in the slightest. This is the crucial thing to understand. The reasons to expect a crack do not rest on RK, or the Muon's wobble or the W Boson's mass. They rest on facts about the universe so large and so plain that no amount of precision testing can explain them away. The model could pass every collider measurement perfectly, and we would still know it cannot be the final word. Begin with what the universe is made of. The ordinary matter described by the standard model, all the quarks and electrons in every star and planet and living thing, makes up only a small fraction of the cosmos. The rest is dark matter and dark energy, unseen and unexplained, and dark matter alone outweighs ordinary matter by more than 5 to 1. The model contains no particle that can be dark matter. The stuff that dominates the mass of the universe is simply absent from the page. A theory that omits most of what exists is, by definition, unfinished. Then there is your own existence. In the early universe, matter and antimatter should have been made in equal amounts and annihilated each other completely, leaving a cosmos of light and nothing else. Instead, a tiny surplus of matter survived, and everything material is built from that leftover. The model includes only a faint imbalance between matter and antimatter, far too small to account for the surplus. Why there is something rather than nothing is a question the model cannot fully answer, and the something includes you. Add the neutrinos, which the original model declared massless, and which experiments showed to carry a small mass after all, a fact the theory had to be patched to accommodate. Add gravity, the one force everyone feels every second, which the model does not describe at all, written as it is in a mathematical language that has never joined with our best theory of gravity. Add the puzzles of structure, why there are 3 generations of matter when one would do, why the particle masses take the wildly varying values they do, why the Higgs boson is so much lighter than the simplest calculations suggest it should be. None of these has an answer within the model. These are not minor gaps at the edges. They are vast holes in the centre, and together they amount to a guarantee. Whatever passes inside the machine, the model we have cannot be the complete description of nature, because nature contains dark matter and gravity, and a surplus of matter, and a host of unexplained patterns, and the model is silent on all of them. A deeper theory must exist, one that contains the standard model as a piece of itself, the way the model contains older theories, and explains what the model cannot. That deeper theory, if it is out there, should leave traces. New particles, new forces, small deviations in precise measurements, where the hidden physics leaks through into the world we can test. The anomalies in this story were guesses at where those traces might appear, and so far they have not held. But the traces must be somewhere, because the deeper theory must be real. The grand silences prove the page is unfinished even though the page itself never lies. So the search is not a gamble on whether a crack exists. The crack exists. We know it exists from the dark matter overhead, and the gravity holding us down, and the very fact that anything material survived. The only open questions are where the crack will first become visible, and when, and what it will reveal when it does. The hunt continues not in hope but in certainty that there is more beneath the page, waiting to be found. Hold your hand in front of your face again, the way you did at the very beginning. It still feels solid and whole and yours. You know now that it is mostly empty space, a sparse scaffolding of particles, built from up quarks and down quarks bound by the strong force into protons and neutrons, wrapped in a cloud of electrons, the whole arrangement following a small set of rules written on something close to a single page. That page is the standard model, and you have walked its whole length, from the matter in your fingertip to the precise gaps it cannot fill. So we can answer the title's question plainly. Has CERN found a crack beneath the standard model? Not a confirmed one, not yet. The brightest hint, the flavor anomaly, faded when the counting was corrected and lepton universality held. The 750 bump dissolved into chance. Supersymmetry never appeared. The heavy W boson stands alone and looks, to most of the field, like a flaw in one measurement. The muon's wobble remains real and beautifully measured, but the theory it is compared against shifted toward it, and the gap narrowed. No single measurement inside the machine has crossed the line that turns a hint into a discovery. The most successful theory in the history of science has so far refused to break in the laboratory, and yet that is not the whole truth, and it would be dishonest to end there, because the deeper cracks are not in doubt at all. The dark matter that outweighs everything we can see is real, and the model has no particle for it. The surplus of matter that let you exist is real, and the model cannot fully explain it. Gravity is real, holding your hand to your side this instant, and the model does not describe it. The crack beneath the standard model is not a maybe. It is a certainty, written across the whole sky and felt in every falling thing. We simply have not yet found the particular place where it first shows through in an experiment we can run. This is the quiet truth the hunt rests on. The page is unfinished, and we know it, and the knowing is not despair but invitation. Every faded anomaly narrowed the search. Every silence taught the field something about where the answer is not. The upgraded machine will gather a haystack many times larger, and the wavering hints will be forced toward a verdict, and beyond it, larger machines wait in the planning. The search goes on because the answer is out there, guaranteed by the universe even when the data is shy. Think of what a real crack would mean when it finally comes. It would be the first glimpse of a layer beneath the one we know, the first new particle or force or principle past the edge of the page, the opening of a door that has stayed shut through every test for 50 years. It would tell us at last what dark matter is, or why matter survived, or how gravity fits with the rest. It would be the beginning of the next page, and the people who find it may already be alive, may already be students staring at this same incomplete and beautiful table. For now, your hand is enough to hold the whole story. The same few particles that build it build the farthest stars, following the same few rules, unchanged since the universe was minutes old. Those rules are very nearly right enough to predict the world 12 digits, and they are not the end of the matter. Beneath them lies something deeper that we have not yet seen, and your own solid, ordinary hand is made of it. The crack is there. We are still learning where to look,